Let's try to solve the second problem from your homework. Again, you are given this simply supported beam AB. There is a uniformly distributed load this time on top. Its load density is given 500 pounds per feet, and you have two external moments at point A and point B to deal with. Both of them are counterclockwise and of same magnitude of 8,000. That's it. So before even starting to plot the shear moment diagram, we need to do the free body diagrams and find all the forces and moments which are applied to the system using equilibrium equations. Well, we're familiar with these two types of supports, right? We know that they don't have any moment reactions, but they do have the vertical reaction. Let's assume that they are upward. If my assumption was not right, then I'll get a negative answer once I find RB, and then I'll correct for that. Let's see. And also at A, we have our vertical force reaction, RA and RB. Well, we use the equilibrium equation. I wrote it here to find RA and RB. Just make sure, well, I just wrote it for you to see. You can pause and look at it. So this is the force balance, and then the moment balance down here about point A. I could have written it about point B. Doesn't matter. I would get the same answer. Upward, I assume that it's positive. So I'm writing RA on RB, and taking into account the force from the uniformly distributed load on top, right? I gotta multiply that density by the length of the whole beam to give me the total, or essentially the resultant force. That gives me the first equation. The second one comes from the moment balance. As I wrote, I'm assuming that counterclockwise here is positive, so that would be my external moment at point A. That is the external moment at point B. RA is, the distance is 0, so it becomes 0. For RB, I have it, and for my resultant force, well, because this is a uniformly distributed load, then I know that the resultant force is going to be passing through essentially the centroid of the loaded area, right? That means the center, like in the mid part, 5 foot away from point A. That's where that 5 comes from. I know you all know that. So solving this second equation for RB, I find RB to be positive 900. That means my assumption was right about upwardness, essentially, of RB. And then I put this back in here and find my RA. That gives me 4,100 pounds. Okay. Alright, so now that, I cleaned the board and I put the reaction forces that we found right there. Okay, they're both upwards, yes. And now we're ready to plot our shear diagram right below the beam. Once again, we start from the very left side at point A and then build up our way toward the right hand side, and take into consideration this distributed load on top and accumulate it as we go on to the right side. First thing, we gotta start from the point force at A, which is RA. That was 4,100 upward. So starting from here, I go 4,100 up and pinpoint that right there, 4,100 pound. Okay, then what's next? Next, we have to take care of our distributive force. Okay, remember this equation, right? Which basically it's telling us that the shear function, or the shear is going to be, the shear force is going to be the integral of the loading function that we will find, or the area underneath this distributive force. distributed load, right? Well, here we have, so I'm going to do this right in here. Okay, so our loading, our distributed loading is given is a constant. So we are trying to write the function for that that load, right? I once again I guess I have to make, so it's a constant, so it would be 500, right? 500 pound per feet. If I put this back in this integral and I integrate it, I will find Vx. Let's do it. So Vx is, don't forget that minus, integral of 500 dx. Well, that's a number. Integral of a number is going to come out as minus 500x. Don't forget the constant plus the c naught. Okay, it's very like simple problem here, so obvious, but I'll go through the steps just to show you all of them. I know you can immediately guess what C naught is, but I will just write it. So in order to find C naught, I just need to know V and X at one point, and then solve it and find the unknown C naught. Here, for example, we know that at point A, which means X equal to 0, V is 4100. Okay, so if I put 0 right there and 4100 right there, I'll find C naught to be 4100. Alright, so I put the function right up there and then get rid of what the derivation of it. So now I have to plot that guy. That's a linear function. Well, we have one point at x equal to 0. We know it's 4100, so I'm giving it a 2 whatever point so that we can plot it. Well, right away we know that that's the slope, that's the intercept, right? Slope should be negative 500. Well, you can plot this however you like. For example, I know that this distributed load is going all the way up to reaching the 10-foot length, so well, I have to find where it's located at here, and it's probably going to intercept my x-axis at one point, so I'll find those and then connect them to each other to plot it. For example, let's see, v equal to 0 at what x is going to pass from my x-axis. That means minus 500 x equal to minus 4100. Let's putting that equal to 0. So x 41 over 5, right? That it will be 8.2. Okay, so that means that x equal to 8.2 here, it's going to be 0. Well, let's plot that. It means that this is like 5, half of it, so 6, 7, 8, somewhere like there is where my second point on that line is going to be located, right? So now, what about when x is equal to 10? So now I'm feeding it x equal to 10 to my v function to figure it out. V at 10 is minus 5,000, well, minus 500 multiplied by 10 plus 4,100, right? So that is going to give me right here. Alright, so that would be minus 900, okay, pound right there. It means right at the location of B, I'm going to show a minus 900, and it's probably higher than that. You see why? Because I have to pass a line from right there. Oops, nope. Let's plot that. Like a line is going to pass through these points. If I could do that. Alright, that's better. Let's erase that. So that point is minus 900. Well, I'm not done yet. I have to take care of RB. RB was 900, right? So I have to go 900 up here. Okay, which I end up at 0. If I don't end up at 0, then something was wrong. So if you actually see that that slope is minus 500, exactly like that. Downward, negative. All right, so for you to see that better, I will do that. Okay, so we're done with that. So now let's move on to do our moment diagram. All right, I cleaned the board again and ready to plot the bending moments, right? Here is one important thing for you to notice is that is the sign convention that we have been talking about. We're about to actually change something a little bit here. And so remember the designer sign convention? Designer. So I'm going to tell you a little trick to maybe make it easier. Convention. Well, the way, if you get expert, you will understand why it works like this. But for now, let's stick to this kind of dumb rule. And that is, if you have moments, right, like that one, this one at point A, that guy, like I have to take care of that on my bending moment diagram, correct? Starting again from left side, I'm going to build up all the moments toward the right side. That was the deal. But now the question is, should I go 8,000 down? Is it going to be minus 8,000 or is it going to be positive 8,000? All right. The idea is that, you remember, if your beam, that is a smiley face that was positive and then it was negative like that, if the bending occurred like that, it would have been negative, right? So here's the idea. When anything that makes your beam basically having a positive curvature on the right hand side of the point, that moment is being applied to, then it's going to be a positive moment. What does it mean? It means that, for example, at point A, that counterclockwise moment, its effect on the beam, just imagine, its effect on its right hand side, right, beam, is that it's going to try to bend this beam like that. I'm very much exaggerating, but that's what it's trying to do. So its effect is a negative, or is a sad face on the beam. It bends it negatively. So that's why we have to go 8,000 on the negative side, minus 8,000. And then from then on, we have to take care of the bending moment that is caused by that distributed load on top, right? All right, to take care of that, the bending moment from the distributed load, remember? We had this. Let's put that right there, maybe higher up, okay? We had that. That means that we need to, when we have the shear force function, then we can put it right there, integrate it, and then find the moment. That's easy. We have Vx right there, so we put it here to integrate it. Alright, so that is what happens if we put that Vx function that we found for this distributed load right there. back in this and integrate it, right? It will give us that back after it's integrated. We have minus 500x. It will come out. It would be like integrating this guy. It would be 1 over x. It would be x 1 over 2 x2, right? Plus some constant. And then the other one, which is a constant number. If you integrate it, it will go 1 degree up, and that's 4100x, right? That C naught we have to take care of. We have to put so the integral of this one is whatever that comes out, then plus a constant, right? We have to find this constant. How do we do that? Using the boundary condition, or doing this essentially. So in order to find C naught, we apply a point that we already know and substitute it. For example, at x equal to 0, we know moment is minus 8,000. Therefore, substituting it in that equation, it will give us C naught. And now I'm as minus 8,000, so I'll put this back in here and write the equation nice and neat up there for the moment that we are about to plot. Alright, so this is our final function, right, that we need to plot right here. The point, we need different points, or you can plot this any method that you would like to, but essentially if you give it a million points, you're going to plot it, right? But we are not going to do that. We just have to pinpoint the important parts and the important points and then plot it. For example, one point, we know that at x equal to 0, moment is minus 8,000, so it definitely starts from there that I'm pointing out in the diagram, right? That blue point at x equal to 0. Then what? Another observation immediately you can make is the fact that you go up here. You remember how I said if dm over dx equal to 0, right, was v, right? Well, if I solve this for x, that means that will give me essentially this point, whatever that x is that we earlier found, right? It was 8.2. I'll write it right there. So that is 8.2 feet. At x equal to 8.2 feet, v was 0. That means my optimum, the optimum of bending moment, is going to happen exactly at that point. By optimum, I mean either maximum or minimum. Here, it's going to be maximum. I know you guys are familiar with how to find x out of this equation, but I'm going to solve it and show it to you. Okay? Alright, let me do this. So I wrote it here. So that's our equation that we just got. The equation of moment as a function of x. That's a quadratic function, right? It has x2, x in it, right? And you know how to solve this type of equation in order to find x. Basically, we want to know where my bending moment becomes 0, because it comes handy. If I know where it's 0, it's where is it intercepting my x-axis over here? It will help me to plot it. Maybe the question is actually asking where along this beam moment is actually 0. The other question is where on this beam the bending moment is actually maximum. Then you have to take that into account when you're designing the beam, the material that you're using. If bending moment is 0 at one point, then you don't need to maybe you can change the diameter of or the property or the type of material that you're using at that part, right? So that is why we are doing all these. Let's go to the next page. So what I wrote here, that's a general form of the quadratic equation that you are probably familiar with. That's like the one that I have memorized. It's like ax2 bx plus c. Then I think of its solution, it just kind of flows as that, like x is minus b plus minus square root of whatever I wrote down in there over 2a. Okay, so just associate or correspond, like make, so I'm having this equation, whoops, where is it gone? Like this guy, I divided by 10. Well, you don't really have to do that. You can directly apply this formula to find the roots. I keep messing up on this board on the app for some reason. It keeps stopping. And so I just decided to make it more simple by dividing it by 10 and a minus 10, so this guy become positive, right? That's just like how I'm comfortable with solving it. It's up to you. Essentially what you get, substituting all the numbers in there, you will find two numbers. Well, it makes sense. It's a quadratic system. X2 is in there, so you normally get two answers out of it. Usually one of them is not acceptable. Okay, just think about it. Go back to your plot and then see why one of these two guys are not acceptable. All right. Going back to our board here. Well, it's very obvious. So one of them was 226, x equal to 226, and the other one was 14.14, right? Well, the whole beam is not more than 10 foot. So this 14.14 is out of the range, but that one is acceptable. So that means somewhere, let's say that is 5, that's like 2.5, right? So somewhere about that range, which is 2.26 foot, my plot or my curve is going to pass through that point. So it started from there, that's one point that we have, and then another point that we find. Alright, the other information that you have to gain from this, as I mentioned it already right there, that my optimum is occurring at 8.2. So sorry, I keep stopping the app. So if I substitute x equal to 8.2 in the function and find the moment, that would be my optimum. Okay, so the question you're asking yourself is, calculating is m for x equal to 8.2. What is it? Well, one thing I can tell you right now is that whatever number you're finding is actually going to be the area underneath your shear curve right there. Well, that is, if you calculate that, I would be 8.2, the base, multiplied by the height, divided by 2, which is the area of a triangular. That is going to give you the maximum moment. Well, you don't want to accept that? Fine. Then you just do what I said. Just substitute x equal to 8.2 in that function and then find the moment. I'll do it for you. Alright, here we go. I calculated it for you. So I put x equal to 8.2 in that yellow equation right here. And just follow the calculation and it finds you 8810, right? 8810 pound foot as your maximum moment, which is going to happen at this point. So we find out, like let's assume that point will give you on this as where should I write it? 8, 10, right? Assume that point is that much, so that would be our third point that we found. Well, it's essentially, at least we know. Let's get rid of all these extra stuff that I put there. essentially you end up getting this plot. Like if you connect them, knowing that this is quadratic, when you're plotting, you know that the slope over there is 0. That's why it's passing through there. Slope here, slope right here, right there, is actually equivalent to that height right up there. That is some, I guess, observation to make. I don't know what color to bring so you can really see, but let's clean this one more time. So slope here, which is 0, is going to be a height up there. Okay, so for example, the slope, whatever this is, this height is right there, for example, if you calculate it, it's going to be equivalent to the slope of this other curve at that point. So is for every single one of them. So maybe you can use that fact to plot your moment equation, but I find it for myself harder. I prefer doing the way I'm showing you right now. So anyway, so we found out our maximum, our moment maximum, and plotted it. So the rest is basically where am I going to end after that, right? Where is it going to? Is it going there? Is it going, I don't know, there? Like, I don't know. So you have to find it. In order to do that, all you need to do is now, instead of x equal to 8.2 right there, put x equal to 10 foot and see where it intersect your y-axis at point B. Do that and find it. I'll write it for you. Alright, here we go. I just did it. I substitute for x equal to 10, finding m for it, which turns out to be 8,000. That is giving me my another point that I wanted for plotting this. So at x equal to 10, right there, my y or my m is 8,000. Therefore, and then I connected them. That would be my plot, something like that. And then you will go, you will take into consideration the last moment, which is again a negative, so it will go down, and then you will end up at 0. Done. And then you extract all the information which is possibly needed for more advanced type of problems, right? So what is the maximum moment? It's at 8,810. At one point in the beam, 8.2. Where does the bending moment on your beam become 0? We found it. Okay. 1.2 mentioned, I think, is that, alright, so you can find the amount of that maximum right there by, as I mentioned, integrating, finding this area, right? But one point to remember is that if you actually find that area, it will give you, so it will take into account from this point all the way up to that point, so you have to take out this 8,000 out of it, right? Just do it. 4100 multiplied by 8.2 divided by 2. It gives, what number was it? It was 16,810. Now, that would be basically giving us the whole moment regarding that curve. So then I have to take out that 8,000 out of it. So that should become 88,008. That should become this number. Okay. Alright. I hope you find this useful.